focus on statistical process control, which is the quantitative aspect of quality management that was discussed in the previous chapter. And in this chapter, the outline of our discussion will include starting with the basics of statistical process control, look into control charts, and actually get into details of the control charts for attributes as well as variables. Then identify specific control chart patterns to see when the process is in control or not. Then getting into the various OM tools as well as the process capability tool, which is to determine if the process is capable of meeting customer requirements. And moving on to our discussion of statistical process control, it is the monitoring production process to detect and prevent poor quality. So statistical process control allows you to constantly evaluate by monitoring the process and to see if the process is producing goods that are in control, in acceptable quality level or not. And how it is done is by taking a sample of those products, which is a subset of items produced for inspection, and control charts determine whether the process is within statistical control limits that have been set based on predetermined level of quality that customer requires. In this case, the process variability can be classified as something that is random or non-random. Random causes of variability, also known as common causes, are inherent in the process, something which we can't pinpoint as to what's causing it. It just happens to be. It's like every time you produce something, every time a process is done, it may not finish exactly. If it's ideally supposed to finish at 60 minutes, it may not every single time finish in 60 minutes. Sometimes it will be 59.5, sometimes it may be 60.5 or somewhere else in between. But you can't really pinpoint what caused it because the variation is so small, it's still within acceptable range. So there's no way to really pinpoint what caused it. Whereas this could be depending on the nature of the equipment or the machinery or the design of the process, the engineering of it. It could be based on the operators' nuances as well as how you measure things. Whereas non-random aspects, the special causes or assignable causes, are specifically identifiable. A student were to try to reach campus, typically if they live 20 minutes away, but on a particular day, they arrive an hour late. There has to be a reason why it took them 3 times the duration to reach something that normally it takes them 20 minutes. If they reach in 20 and a half minutes, then there is no explanation needed. That half minute could be part of the random variation. Maybe they just got one additional red light. But if they end up reaching 40 minutes as compared to 20 minutes or 60 minutes as compared to 20, that's definitely, there has to be better have an explanation for that. And that's the identifiable or correctable thing. Maybe there was a accident on the freeway, or there was some sort of construction going on. So for the future commute to work, commute to school, a student can then plan that tomorrow they will end up taking a different route so as to avoid that construction jam. So in this case, this could equipment out of adjustment, defective materials, any specific cause. It is the machine that was messed up. Maybe the car is breaking down, had a flat, and that's the reason for the problem, or the car is giving me starting problems, or the defective material. Maybe the oil that I put in was not the right consistency, changes in parts of material that may have caused it, or broken machinery or equipment, operator fatigue or poor work methods, error due to lack of training. So these are very very specific identifiable causes. That's why it's non-random sources of variability are also known as assignable causes or special causes, whereas random ones are called common causes. So statistical process control in quality management, the idea it uses, typical uses are to identify if the process is in control. Also, it's used to identify problems in order to make improvements and contribute to the TQM goal of continuous improvement. And in this particular case, one way to look at quality characteristics, which can be identified as variable as well as attribute type of data. So any type of data that you're collecting can be labeled as either variable or attribute. Variable data is any type of characteristics that can be measured. So a person's weight, a person's height, or distance in length. So those actually has specific units, something that can be measured. It may be in whole or in fraction numbers. So in this case, height, somebody's height could be 5 feet 8 inches or 5 feet 10.5 inches. So it could be in fractions as well. And typically, it's in statistical distribution, it's a continuous random variable. Whereas attribute data is characteristics that cannot be measured, it can only be counted. For example, the number of students in a class can only be counted. You can say, okay, there are 40 students in the class, or today there are 41 students in the class. You cannot say there are 40 pounds, or etc. So in this case, typically you can say of all the students in the class, how many received a passing grade, or how many received a failing grade. So that is, you can easily count to identify the defects. So in this case, there are two different categorizations that you can do for attribute data. You can classify them as good or bad. So all the students, how many of them passed versus the remainder automatically means they did not pass. So that's a good, bad, go, no go, pass, fail. Those will be all examples of credit, no credit. Those will be all examples of that classification. The second type of classification is where you can only count the defects or observable. Only one type of thing is observable, the defects, but non-defects are not observable. So in this case, you can only count the number of defects. For example, on a 1 mile stretch of road, how many potholes? One can easily count that if they had the time and the inclination to do that. But you cannot count the number of non-potholes on a road. You can check radio works, but that's defect-free. But you can count the number of defects if radio is not working. For example, there are scratches. There is a short in the circuit. The antenna is missing, but there is no way to count the non-defects in a radio. So in this case, both of them had different type of charts associated with that. Categorical, these attributes are categorical. Either it falls in one category or the other, but not both. And then these are discrete random variables. Now SPC can also apply to services. Nature of defects is different in services. Service defect is a failure to meet customer requirements. So in this case, typically SPC can be used to monitor the time and customer satisfaction. Whether customer satisfied, yes, no, can be used there, or how much time does it take to satisfy the needs of the customer? Time taken to attend a call, to the successful resolution of a complaint. That could be also a continuous random variable in that case. You can see several examples of how statistical process control can be applied to services. You can apply them in hospitals, as the list is provided to you in the PowerPoint, grocery stores, airlines, fast food restaurants, catalog companies, insurance companies, among others that make extensive use of statistical process control in this case. Where to use control charts? Typically, we use them in processes that have a tendency to go out of control so that we can constantly evaluate and see if things are going out of whack and we need to stop and revise the process to fix things. It's almost like having a fuel gauge which has a reserve light. So that's equivalent of constantly checking if we will run out of gas, because if our consumption is uneven week by week, the variability is there in our use of vehicle. We want to be apprised of when we will run out of gas. So we want to have, so same logic, you want to use the control charts in those scenarios where variability is there, process variability is there, and you want to make sure if there's a tendency to go out of control, you can't afford to. It's pretty expensive, harmful, to human beings or to the material that is being used, and expensive if things go out of whack. You may end up producing the wrong product, or somebody may be in harm's way as workers if in case the machine becomes overheated, or somebody may end up lose a daily wage in case you run out of material in those cases. So it makes sense to use control chart in those scenarios. Now, in terms of, you can see some examples that are listed in here. I'll just go through a couple of them just to illustrate. At the beginning of the process, because of waste to begin a production process with the bad supplies. So it makes sense to actually use statistical process control early on at the start of the process, because you don't want to actually start producing the product with bad parts. So it's almost like incoming quality control. It also, before a costly or irreversible point, you also want to make sure any input into a very expensive process that you're doing should be all the input that is going in there, material, work, putting in is of good quality. And before and after assembly or painting operation, that might cover defects. So you want to make sure everything is acceptable before you unwittingly send out a defective product to customer, and before the outgoing final product and service is delivered. Okay, those are several examples of that. Control charts typically are a graph that monitors process quality. Control limits typically are upper and lower control limits. What is the upper bound and the lower bound associated with this control chart? And for attribute charts that we mentioned for items that can only be counted, we have P chart, which is the proportion chart, and the C chart, which is the number of average number of defectives chart. And for the variable chart, we have the X bar, which is the mean chart, and the range chart, R chart, which is looking at the variability in this case. So typically, you have a process control chart where things are being monitored, and as long as they stay within the shaded region of upper and lower control limits, that's considered normal or random variation. So this is okay, statistical state of control. So even though this is varying, ideally we would like everything around the mean, but it's slightly below the mean, but it's still acceptable because it's still above the lower control limit. Or this number is still below the upper control limit. So those are all acceptable till we reach this point, and that's out of control. And for out of control aspects, there better be a assignable cause that we identify and then remedy that so that we can bring the product process back in control. Okay? So that's the way to look at it. And in this case, one typical use that we, for normal distribution that is used in here, you can use plus or minus 3 standard deviation, which is takes into account 99.74% of the data. Or you can use 2 standard deviation, which is 95% of the sample will be within normal range. So typically, unless otherwise specified, most of the time in industry, it's always the plus or minus 3 standard deviation that is used, which is 99.74%, which is virtually everything should in here is normal, and that is what you're trying to capture in this case. So whenever you hear z value of 3 is the standard, the default value, and unless otherwise specified, that's what you'll be using. And sometimes they may say calculate 2 sigma. In that case, you'll put z of 2. But otherwise, typically in industry, you always end up calculating 3 sigma control limits, which is z value of 3 that is being used. So process typically is in control if no samples outside the limit, most of the points near the process average, about equal number of points above and below the center line that you're thinking, and those are the patterns that you are looking for, and points appear randomly distributed around the process average. So typically the process control chart for attributes is the P chart, which uses portion defective in a sample, and then out of the total, rest are the portion non-defective. And the C chart uses the number of defects in a sample that you have. And so let's go ahead and look at the P chart. P chart, the formula is pretty straightforward using normal distribution. You have the average plus Z times the standard deviation. So that's number of standard deviation from, in this case, Z. If it's not given, it's automatically assumed to be 3 by default, as I mentioned earlier. So in this case, this is a binomial distribution because you can have only 2 possible outcomes. One is a pass-fail. So in this case, percentage defective would be percentage of the students that did not pass the class, or percentage of computers that failed a test. So they are non-saleable. So in this case, we use the formula for binomial, calculating the standard deviation of a binomial variable, which is P bar times 1 minus P bar over n square root. So this is the binomial distribution value of mean and standard deviation that is calculated. And in this particular case, let's take an example that is given in your textbook, where you have a sample of 20 items, which is number of defectives are calculated. So in this case, 20 sample of 100 pairs of genes. So in the first sample of 100 genes, only 6 were found defective. Out of 100 genes, pairs of genes, only 6 pairs were found to be defective. That's 6% defective. In the second sample, all 100 genes, pairs of genes were considered saleable. So 0 defective, that's 0%. Third one, 4 pair of genes were found defective out of 100, that's 4%. So similarly, you calculate all the way to 20th sample of 100 genes. Out of these, 18 pairs of genes were defective, that's 18%. So you're calculating this last column, and once you take that and average it out, you get a P bar, which is the average proportion defective. So in this case, P bar is total defectives, which if you were to add all the portion defective for number of total numbers that you have, which is adding up the 200, and that divided by 20 samples times 100 genes in each sample. That's 2,000. 200 over 2,000 is 10% is the average proportion defective. So in this case, you have P upper control limit is P bar plus Z times square root of P bar times 1 minus P bar over N. So in this case, 10% plus 3 times you have the remainder of the formula. And that, when you take this number and add it to 0.1, this gives you 0.190. And the same thing when subtracted from 0.1 will give you the lower control limit, which is, again, so this number comes out to be 0.09. So 0.1 times 0.09 gives you, minus 0.09 gives you minus, gives you 0.01. So that it gives you the actual range. So this is 0.01, and that's 0.19. So you guys can see the difference the ranges, upper control limit and lower control limit. And in this case, now you can actually indicate, so this is 6%, that's the first value of the proportion. Second one was 0, then third one was 4%, and so on and so forth. The last one was 18%, which is over there. So in this case, you can see sample number 2 and sample number 19 is out of control. Also, you notice that it's not random. It's consistently going up as the production is processed over the day. Every hour that you're taking sample, the machine is heating up or the process is producing more and more defects. So something to note. So it's not, something is not normal about it. So it's definitely a cause that can be either identified related to employee that is not paying attention as the day goes on, or the machine that gets heated up and is going out of whack. Something has to be fixed. So you can see this is not representative of the sample, and the second to last one as well. So that has to be, so it's definitely not in control. It has to be remedied. Let's look at an example of C chart. And in C chart, it's a Poisson distribution instead of, in P chart, we talked about the binomial distribution, because for each outcome, you can identify, label it as yes, no, pass, fail, go, no, go, on, off, saleable, non-saleable. So that's the binomial, because there are 2 possible outcomes for each event. In this case, we can only count the number of defects, but we cannot count the number of non-defects. Because of that, that is the number of customers that show up in an 8-hour shift, you can count, but you cannot count the number of customers that did not show up. So in that case, we use Poisson distribution. And for Poisson distribution, again, using the same formula for upper and lower control limits. So you have C bar plus Z times the standard deviation of that same C. And for Poisson distribution, the standard deviation is calculated to be square root of mean. So that's the, it's an easy formula in this case. And C is the number of defects per sample that you have. So let's look at an example of that. You have number of defects in a 15 sample rooms. So if you were to think of a hotel where after the maids clean up the room, inspector may go in each room that has been cleaned by the hotel maid and actually identify if there was something that was not done correctly in terms of cleaning of the room. So in the first room, they identified 12 defects. In the second room, they identified 8 defects. Third room, 16, and so on and so forth. On the 15th room, they identified 15 defects. Altogether, that's 190. So 190 divided by 15 rooms, that gives you average number of defects is 12.67. So in that case, square root of 12.67 will give you the standard deviation. So now Z value of 3, as I said by default, you're looking at upper control limit of 12.67 plus 3 times the standard deviation, which gives you 23.35. And lower control limit is 12.67 minus 3 times the standard deviation, which is 1.99. So in this particular case, you can see you have a lower control limit 1.99, upper control limit 23.35, and most of the data that, as I said, this is the average 12.67. The first room, there was a number of defects were 12, then it went down to 8, then it went up to 16 or 17, and so on and so forth. So you can see as you draw this chart, you can see the process is well within the upper and lower control limits, and its trend is pretty random. Some items are above and some are below. There's no significant identifiable pattern to it. So it can be considered as in statistical state of control. Let's move on to a discussion for and scratch that. And this wraps up part 1 for our discussion of statistical process control. in the next part, we'll focus on the variable control charts and process capability. Thank you.